Thank you for the introduction, and thank you for the invitation to speak here. It's right before lunch. You guys have all been sitting here, so I decided to keep my talk a little bit lighter than some of the last two talks. The last slide will have a list of references to papers, so if you want to go in and see all the actual equations and theory, that stuff's all out there on the web. But what I wanted to talk about first was well, I wanted to start with a video, and so if I'm going to start with a video, it means I have to talk about some type of application. So the type of big data that I work with are data that come from physical simulations. So we often display these as pictures, but what this is a physics simulation of a cylinder with some type of complex internal geometry. And what we're doing is we're heating this from one side, and we're seeing what parts of the cylinder get hot. So there are different types of materials in the cylinder, and we want to make sure that the important bits inside don't get too hot. So this is an abstract representation of all sorts of complicated geometries that might show up in different types of applications. But what's interesting about these data is all the simulation data sort of happens inside this cylinder here, and we have points at time, space, and usually different types of features at each point too. So I'll describe, or I'll focus a little bit more on one particular study we did. And so we're going to go through a couple of applications, why we need tall and skinny QRs, and then we'll show you how we actually do them. So the particular study we did most recently was we had a big brick, and this brick was composed of two different materials. So there was something that sort of looked like steel, and there was something that sort of looked like foam. So if you look at this brick here, you can see that there are these bubbles inside of it. So those bubbles are foam bubbles. And what we want to do is understand how heat propagates in this brick if we heat one end. So if we apply heat on one end, and then we look at the temperature on the other end. So now, just taking one of these bricks with a set of positions of these foam bubbles and running it through a nonlinear heat transfer code at Sandia National Labs takes about 5 hours on 8 processors. So this is using one of their big thermal codes. That's probably as fast as these things can go. What we did was we ran this code 8,192 times, where we varied the position of the bubbles and the size of the bubbles. So in particular, we looked at 64 different bubble sizes, and we looked at 128 different positions of every bubble. So if you multiply those two out, you get 8,192. And if you look at how many CPU hours we spent doing this, it's around 400,000 CPU hours. So this actually output about 4.5 terabytes of data. That is stored as net CDF files. And what we wanted to do is do some type of global analysis, or what's called in the literature model order reduction on this data, to build an approximation for what this model does, so that we can do not 8,000 runs of this, but around 100,000 runs without burning about 100 times as many CPU hours. So that'd be about 40 million CPU hours, I think, if I did that right in my head. All right, so we've got this 4.5 terabytes of data, which actually, if anyone else wants to play with this, or this would be a useful test set for other people, it's out there on the web. So this is at the Open Science Data Cloud, hosted at the University of Chicago. So if anyone would like large spatiotemporal distributed data sets, and lots of them, they're all there. So what are we really trying to do? Well, we're trying to figure out what the temperature looks like at that end plate there. So we heat it from one side and we look at the other case, and we're looking at how much of that final surface is sort of too hot. So as we vary this bubble size, there's a regime where it looks like an insulator, so there's not much hot, and then there's a regime where it doesn't look like an insulator. And what we want to do is predict this threshold based on all of this data. So how do we do it? Well, we actually end up constructing a nice, cool little matrix equation. So we actually treat each simulation as a column of some big data matrix A. Actually, it turns out we treat 128 of these simulations as a column of this matrix A. So we concatenate all of the different bubble locations together into one big matrix. So we end up with a 5 billion by 64 matrix out of stitching all of these simulations together. So this is about 2.2 terabytes of data. If you just look at the double precisions, if you actually store it in a real system, there's a little bit more overhead, but let's just say it's 2.2 terabytes. Then we construct an SVD of this. So we get an enormous matrix U, we get sigma and V transpose. So what we're going to talk about after we discuss the application is how you do this SVD on MapReduce, and a couple different choices for how you might do it depending on your application. Once we have the SVD, we actually just get out the components of U corresponding to that face. So when we put this simulation, and every point in this brick becomes a row in our matrix A. And so we can just extract a small subset of those and do a whole bunch of analysis on that subset in order to figure out how this phase transition happens. So once we have that, we can do it on a laptop, and that's what my colleague did after we extracted that subset. And so what do you see? All right, so the blue line is the true phase transition between these two regimes. The red circles are what we get from our method, and the green dots, which don't show up all that well, but I apologize about that, that's what you get if you don't do the SVD step. So you might say, well, why bother with all this big expensive SVD things? Why not just go in and get the data from that simulation at those points and do some type of analysis just on this final surface you're interested in. So ignore the fact that there's the rest of the simulation is out there. This is really cheap and expensive. There's no SVD involved. Well, the reason you don't want to do that is you get the wrong answer. So you get it more or less right. So there's a laser pointer on this thing somewhere. So you get it more or less right. That is, if you look at this plot, it kind of looks the same, the green dots. But then again, these are actually quite a bit different. So you sort of get it in the wrong position, and our SVD technique gets it much better. So the other thing you can do with this SVD technique is actually predict what new simulations look like. So suppose you actually wanted to do those 100,000 studies on this. Using that same idea, you can compute some type of interpolation of the singular values and vectors themselves. I'm not going to go into detail just because that's a different talk. But what happens here is you can compute a simulation about 100 times faster via this model we construct on the SVD. Now, it's an approximation, but it comes with an error estimate. So here's the true error, and here's our error estimate for a representative piece of this brick. And so what you can see is where this thing is high, you do tend to see high error. So this is sort of the temperature offset in degrees Celsius, I believe. Moreover, you can see that over sort of all, so S here are the sizes of bubbles. So as we vary the size of bubbles, you can see sort of how our error looks. And so we get about 2 digits of accuracy in this as we vary this, and it goes about 100 times faster. So the idea here is you can do this big, expensive, big data analysis and then construct a model that you can evaluate 100 times faster. So we've seen a lot of these ideas. Sergey mentioned core sets yesterday. This is what's called reduced order modeling in simulation literature. But you can do these things a lot faster, and so that's why we want to compute this big SVD. So let's see, how am I doing on time? Do I have time for this video? I think so. So I should say that the current stuff is small. What we want to be able to do is to scale up to data that looks like this. So this is a large eddy simulation. So I believe it's about 100 time steps, where every time step is about 4.5 million points. So here we're doing an SVD for a different reason, but we actually want to do multiple simulations that look like this. At the moment, we're just taking this 45 million. It's actually so 45 million data points, 1,000 time sets, but each data point has 4 different features associated associated with it. So it's really 160 million. So here they just did a single SVD of this data set in order to figure out these bubbles that come back up. So this is a simulation of a jet engine. And what they want to do is figure out a way of making this jet engine quiet or on military installations. It turns out that the hearing protection we can apply isn't sufficient to enable people to work for more than a couple minutes on an aircraft carrier deck. And if they can make a jet engine quieter, you can get people out there longer. So what they did here was a single SVD of this 160 million by 1,000 matrix to find those bubbles that came back up. This helped them understand where the acoustic energy was going and taught them a couple things that they didn't know about how the acoustic waves were propagating in this particular jet. So I should also say that this was done by a guy who usually runs simulations on 1.5 million cores out at Lawrence Livermore National Labs, and he was very excited to use our MapReduce implementation of SVD just because he didn't have to deal with the complexities of manipulating data in MPI. This is not a particularly fun thing to do if you've ever had to work with that in MPI. Okay, but now we've been talking about big data, so I have a question. Is this big data? So I said 4.5 terabytes. Sergey yesterday said that big data has two properties. So it's too big for one hard drive, so we can check off that one. The other thing he said was that there's a skewed distribution. Now, I don't know what the skewed distribution in here, so I'm not sure we qualify as big data under that one. But here, I think Sergey didn't tell us that he was really talking about an acronym. So he was talking about big data. So this is big internet giant data. So Google, Yahoo, everyone else. What are we looking at? We're looking at big data or big engineering data. All right? So a little bit different. We don't have quite the skew, but it's still very large. All right. All of the matrices we've seen are fairly tall and skinny. I said 5 billion by 64. I said 45 million by 1,000. What's an operational definition of tall and skinny? Well, so Austin has my favorite, which is that you can treat order n squared as a constant, effectively. So order n squared is so small compared to m, or your total data size, that you can basically ignore any communication of order n squared work. So Jim will give us a talk on Thursday, and he'd probably say something about moving data from from slow memory to fast memory, and how big the sizes are and things like this. I just think of this as really what you should think of. So all of these problems, n was approximately at most 1,000, so 1,000 times. So 1,000 times 1,000 is a million. 8 bytes per entry there is about 8 megabytes. I think the cache on my phone is now bigger than 8 megabytes or something like that. So these are small problems, and you can compute and transfer them extremely efficiently. So the key routine we're going to use to do all of these big SVDs is actually a QR routine. So the title of the talk was doing QR, and so this is why the title of the talk is really QR and not SVD. So what is a QR, and why does it help us get an SVD? Well, the QR of an m by n matrix is a decomposition into an orthogonal matrix times an upper triangular matrix. So Q is orthogonal, R is nice and small, so it's n by n, and Q is m by n. So R is this nice tiny n by n thing we can move around efficiently. Q is big, nasty, and bad. So suppose we actually had a QR. How does that help us get an SVD? Well, this is an old idea called RSVD. What you do is you first do a QR of your matrix A, so you get Q and R, and then you do an SVD of your matrix R. So that'll give you a sigma V, and it turns out that if you just take the product of U from this matrix R and multiply it against the matrix Q, you actually get out the SVD. So the SVD is unique up to some sign properties, and this will get you one of those SVDs. So this is what we're going to do when we compute these big SVDs. All right, Michael was telling us about a random sampling procedure. Other people were telling us about MPI implementations. There are good MPI implementations about this. There's a library called Scale LAPACK that's been optimized to death over the last few years. What's left to do? Well, if your data is not in an MPI cluster, or your data is somewhere else, or you don't even want to work with your data in an MPI cluster just because it's you don't have enough space in the parallel file system or something like that, you can't always use MPI for some of these big data things, or it just might be too costly to get your data into the MPI cluster in the first place. So what we're going to do is we're going to look at using a MapReduce implementation of this. So how do we store tall and skinny matrices in MapReduce? We're going to do the obvious thing here. We're going to take our tall and skinny matrix A and let Hadoop divide it up into blocks. So we're going to store either a single row as each record of this. And so I should say that these are all dense problems. There's no sparsity to take advantage of here. So we're basically going to store our matrix as a collection of records where every record is a row. What Hadoop does, or what a MapReduce system does, is it breaks it up into all sorts of different blocks. So effectively what we're doing is we're taking our matrix and computing some type of row partition of it. So this is all done by the system, although we might actually store B by n blocks, where B is something not too big, maybe up to n. So then every matrix AI is going to be an input to a map task. I'm not telling you guys about MapReduce just because I wanted to go over some videos instead, and we've seen a lot about MapReduce already. So if you're not familiar with it, please come up and chat with me afterwards. There's a couple of backup slides. All right, so still, isn't this relatively easy to do? What's the big deal? We want to compute A is equal to QR. We know if we form the normal equations, A transpose A, that's a nice small matrix. Everything involved there is n by n. I've said that that's free or cheap. Once we have that, we can compute a Cholesky factorization of A transpose A. That actually gives us the R in QR. And then we can compute Q by AR inverse. So how does this work in MapReduce? We take, oops, there's an extra index there. We take our little matrix A1, and we just compute A transpose A. That's something we can do locally, and that's not necessarily n-squared work, but it's fairly efficient. Every mapper outputs its little local n by n block. I said that was cheap. The reducer just sums all these things up and computes a Cholesky factorization of them, and then we just map the matrix AI back to AIR inverse. So this is great if your problem is well-conditioned. So if A is a well-conditioned matrix, this is a fantastic algorithm. But if A is ill-conditioned, and even modestly so, then your R matrix is not going to have much accuracy left. And a bigger problem is a lot of applications actually need Q to be numerically orthogonal. So if you do this, Q is not going to be numerically orthogonal. So what actually happens? So here we're varying the condition number of our matrix. This is sort of how sensitive that matrix is to small changes. Here we're looking at the numerical orthogonality of Q. This matrix here is 10,000 by 10. These problems just get worse if your matrix is bigger. So if your condition number is 10 to the 8th, that's not all that large for some types of applications. Then you've basically lost all orthogonality in Q. So Q is very far from an orthogonal matrix. So if you actually need an orthogonal Q, this procedure isn't going to work. So we're going to talk about 4 things that are better in the 9 minutes I have left. So that's about 2 minutes each. It's a good thing that 3 of them are basically riffs on the same idea. So we can go through those pretty quickly. So these are all based on a communication avoiding QR algorithm that Jim Demmel proposed. And they all give us much better stability results. So the first thing is essentially a riff on the same idea of using AR inverse. So here there's an incredibly simple procedure to get the R factor numerically accurate. So if you get R numerically accurate, that is, you avoid the normal equations, then you can get not necessarily good results, but results that are orthogonal out much further than the A transpose A algorithm. So these 2 algorithms cost exactly the same amount up to small numbers. Now, if you actually want orthogonal things, we're going to discuss 3 algorithms. Number 3 here is actually kind of cool. It incorporates some ideas from the randomized matrix literature on sampling. So this and this actually cost about the same amount too. So if you want nearly full orthogonality, you can get it at not too much extra work. We can't necessarily prove that this one works, unfortunately, so it's kind of a heuristic, but it's a heuristic that would work for a lot of applications. So just to be a little bit more precise here, what happens if we just want to read a matrix A? So this takes about 253 seconds in our MapReduce system if the matrix is about 200 gigabytes. If we want to write out the matrix A, it takes about 1,000 seconds. If we want to just compute R using our new algorithm, it takes about 500 seconds. So it's about twice as long. If we want to go in and get Q is equal to AR inverse, that's with nothing fancy, that's using the old algorithm. So that old blue line that wasn't precise takes about 1,600 seconds. And if you want to get a provably numerically orthogonal A, it takes about 3,000 seconds. These codes are all available, so Austin's done a great job, who's back in the audience there, has done a great job of actually writing these things up and documenting them and making them useful for other people. So feel free to use them. What's the big idea? So the big idea here is if you do a QR iteration, it's a real reduce operation. So if I want to compute a QR factorization of the matrix A, and I had my matrix A in 4 blocks, then what I can do is I can do local QRs of every block. So I take A1, I do a QR, that gives me Q1 and R1. If I do A2, I get Q2 and R2, Q3 and R3. So I can do one iteration of this and get something that is not quite a QR factorization yet, but this matrix A was originally 8n by n. Now it's down to 4n by n. So I've reduced its size by a factor of roughly 2 in this case, and this is isn't necessarily the best or the best case for this. But I can just recurse on this 4n by n matrix. So if I compute a QR factorization of that, then the product of this Q and this Q, again, this can be done locally very easily because this has a block diagonal structure, is the QR factorization of the matrix. So you can stitch these QR factorizations together and actually compose them to get a QR factorization of the entire matrix. So this is why this algorithm is a great fit for MapReduce. You can also show that adaptations of the same idea give you ways of minimizing communication for any type of QR algorithm you want to do. So that's what Jim Demmel did in their 2008 paper. So how would this work if you were to do this not, or how would this work if you were to do this just on one machine? Well, what you can also do is just read in, say, the first block of the matrix A, compute a QR of that. That gives you R. Read in the second block of the matrix A, compute a QR of that. That gives you another R, and just keep reading in blocks and updating your QR. So you get some really complicated Q here, but you can do these things really efficiently. What we do in MapReduce is just combine these two ideas. So within each mapper, we're reading blocks of the matrix A and computing QR factorization. So we can do this in roughly, I think we usually read 4 times n rows of the matrix A and then compute a QR factorization. So that's roughly time n squared. So each of these things is basically a constant time operation. This n squared is free way of looking at the world. And the same thing for updating all of these. Between mappers, we just compute a QR within each mapper, and then in the reducer, we send all of our small matrices R back to one computer and have them compute and have that computer compute a single QR factorization. So we're just taking that reduction tree and looking at it on MapReduce. Now, I said it. So one problem with that algorithm is you actually have to send everything down to one reducer in the end. So if you had a really large input matrix, there's some properties of Hadoop that make it painful to actually communicate data around. So occasionally you have to add an additional MapReduce iteration for efficiency. So this is a detail of some of the implementation. So if you have questions about this, let me know afterwards. But there are some complexities with doing this on very, very tall and skinny matrices. This gets you R. How do you get Q? So again, that was this algorithm 1 here. How do you get Q? Well, you do AR, so algorithms 2 and algorithm 3 are just doing AR inverse with an additional step of iterative refinement. So I'm not going to describe how to get AR inverse. You just basically take R, it's n by n, it's tiny. You just distribute it to all processors and then just compute AR inverse with one additional MapReduce iteration. How do you do iterative refinement? You just repeat this entire procedure again. So in iterative refinement, you compute Q. Q is not numerically orthogonal, but then you compute a QR factorization of that Q. Because it's not numerically orthogonal, you get a non-trivial R, and you just repeat this entire thing. So it's kind of like taking a Newton step, if you're familiar with some of these other ideas. So you just repeat the entire thing again. It's a folklore theorem that 2 iterations of this are enough. Every time I give this talk, someone suggests that it's attributable to a different person. But there is a lot of evidence that suggests that 2 iterations of this are enough to get a numerically orthogonal Q. The problem is you might not want to do this entire procedure twice. So what could you do instead? So here's where the randomized guys come in and save our butts, I guess, in this case. If you just grab a random sample of your rows, and this might be actually difficult to construct in Hadoop. So if there's some questions about how to do this or why we can't really why we can't actually do this in Hadoop, come up and talk to me afterwards. But you can approximate this in Hadoop pretty efficiently. So you grab a random sample of your matrix A, and then you compute a QR of that matrix. And the idea from blend and pick and what Michael talked about was that you can use these to precondition your problem. So what we're doing here is we're using that random sample of rows to precondition the ill conditioning of our problem. And then if you just do one step of TSQR, you can sort of view this as pseudo-iterative refinement. You're not doing a full QR up front, but you're doing a full QR at the next step. And this is good enough to get you actually numerically orthogonal results all the way along here. And it actually beats exact iterative refinement, although there's some details here. The problem is we can't prove that you get numerically orthogonal results here. For some applications, it's nice to be able to prove that up front, in which case we really do have to go through a somewhat expensive procedure of storing a lot of intermediate output data Q, tracing where it comes from, and feeding the data back to this. So there's a way of doing this in MapReduce. Basically, you just have to tag some of your outputs, which actually took us a while to get right, because it's not the most natural thing to do in MapReduce. So we have all sorts of numbers on this. I'm out of time. We have a performance model that shows you how well you do versus how well you might be able to do in theory, and we do pretty well. So for matrices with lots of rows, it takes a while to do our exact algorithm, but we have all sorts of approximations in case you don't need that. So papers here, we've got some. Oh, it turns out I've got some other alternative acronyms for big here. So in case you want other interpretations of big, it could be bloody imposing graphs, building impressions of ground truth, blockwise independent guesses, or my personal favorite is this one. So best implemented at Google. Anyway, with that, there are other questions and references here. So thank you.
Let's take one question.